Welcome to this explainer. If you're an early career researcher, a PhD scholar, or an MBA student, you already know the feeling. You're staring at a massive data set, and it just looks like the Matrix, right? Well, today we're jumping straight into a cinematic, comic-style case study to fix exactly that. Imagine an overwhelmed PhD student staring blankly at a screen full of data points. Enter their supervisor, Dr. Mira. She's about to guide the student through one of the most pivotal and honestly kind of misunderstood stages of fsQCA, the truth table and Boolean minimization. Let's get into it.
Dr. Mira kicks things off by establishing the absolute core philosophy of this entire methodology. She asked her student to completely stop thinking like a traditional statistician for a second. Look, we are not running a standard regression here. We aren't hunting for that one single magic bullet, that one strongest variable that drives an outcome. Instead, we are searching for causal recipes. We want to find these specific patterns and combinations of conditions that, when mixed together just right, consistently produce the outcome we're studying. It is a massive, fundamental shift in how we view causality.
Part 1. Building the truth table, from cases to configurations.
Okay, so picture our students staring at this totally chaotic sea of cases and conditions. You've got fuzzy set scores for countries like Sweden, Norway, Denmark. Just numbers like 0.8, 0.4, 0.6 scattered literally everywhere. The student is completely lost. But Dr. Mira steps in and introduces the ultimate organizing tool, the truth table. She explains we have to take these raw cases and arrange them into clear, distinct configurations based on their set membership patterns. Basically, we're bringing order to the chaos.
Now, the golden mathematical rule for actually building that truth table is just incredibly elegant. The formula? It's simply 2 to the power of k. If k represents the total number of causal conditions you're throwing into your study, your truth table is going to automatically generate 2 to the power of k rows.
Let's break down exactly how that scales. If you've got 3 conditions, let's say leadership, training, and digital readiness, you're going to have 8 possible combinations. That's 8 rows. Bump that up to 4 conditions and it jumps to 16 combinations. 5 conditions? Now you're looking at 32. What this means is that absolutely every single logically possible combination gets its very own row. Imagine each row as a totally unique potential recipe. For instance, one row might be leadership present, training present, but digital readiness absent. Every single base is covered.
Part 2. Frequency and consistency thresholds.
Of course, in the real world, not every single one of those logically possible rows actually means something. Some of those theoretical recipes might not have any real-life cases attached to them at all. So Dr. Mira points out that we have to filter our data using 2 absolute must-have thresholds. Think of frequency as a funnel and consistency as a bullseye. The frequency threshold asks, hey, do we even have enough cases for this recipe to matter? If it's a small sample, you might literally just need 1 case. But for a large sample, you'd probably set that threshold to 5 or 10 cases just to be sure it's not a total fluke. Consistency, on the flip side, asks, do the cases in this row actually hit the target and produce the desired outcome reliably? Normally, you're looking for a raw consistency score of 0.75, or ideally 0.80 or higher.
When you get into the software's truth table window, well, this is where the magic actually happens. By applying those frequency and consistency thresholds, you're essentially grading the recipes. You assign an outcome value of 1 to the rows that pass these strict tests, meaning they are genuinely sufficient for the outcome, and a big fat 0 to the rows that fail. You are literally separating the signal from the noise.
Section 3. Resolving contradictory configurations.
Right as the truth table starts looking perfectly organized, boom, a red alert flashes in our comic case. The student hits what's called a contradictory configuration. This means the exact same recipe, the exact same row of conditions leads to the outcome in some cases, but totally fails to produce it in others. It's a blatant contradiction. Now, you absolutely cannot just ignore these alerts. Dr. Mira steps in and hands the student a troubleshooting checklist. You have to actively investigate. First, go back and review how you calibrated those fuzzy sets. Double-check your case coding for accuracy. Then you really need to step back, reevaluate your theoretical logic, and see if there are any hidden contextual differences between those specific cases that your current model is just completely missing.
Moving on to Section 4, Boolean Minimization and Quine-McCluskey.
Okay, so with the contradictions finally ironed out, it is time to bring in the heavy machinery. Those rows that passed our strict tests, they're called primitive expressions, and honestly, they're usually really long and clunky.
So Dr. Mira tells the student to fire up the Boolean Minimization engine. This mathematical engine relies on a really clever algorithm called Quine-McCluskey. Its whole job is to take those giant, complex expressions and automatically delete the totally irrelevant variables, simplifying them down into short, punchy causal recipes.
Let's actually walk through how this logic works in practice. Step 1. Imagine recipe 1, where condition A and B and C are all present and it leads perfectly to the outcome. Step 2. Now look at recipe 2. Condition A and B and the total absence of C also leads to the exact same outcome. Step 3. Since having condition C or not having condition C literally doesn't change the final outcome at all, the Quine-McCluskey algorithm spots that. It realizes C is completely irrelevant to the specific pathway, so it elegantly condenses the whole recipe down to just A and B. Boom! That is Boolean minimization in action.
Section 5. Reporting the 3 solutions.
As the minimization engine finishes its thing, the software generates your final results. But here's the catch. It doesn't just hand you one neat answer. It gives you 3 completely distinct types of solutions. Dr. Mira lays out the options for our student. First up, the complex solution. This one takes absolutely 0 mathematical shortcuts and uses no logical remainders. It's incredibly detailed, but usually way too long to be practical. Second is the parsimonious solution. This one goes completely in the other direction. It takes every single possible mathematical shortcut to give you the absolute bare-bones core conditions, even if those shortcuts don't make any real-world theoretical sense. Finally, we have the intermediate solution. This is the Goldilocks solution. It carefully balances the raw math with your actual theoretical knowledge, using only the logical remainders that make genuine sense.
So faced with all that, what does our PhD student actually write in their research paper? Dr. Mira's advice here is absolute industry standard. You always report and interpret the intermediate solution as your main narrative result. It is by far the most theoretically sound. But you definitely don't just toss the other 2 in the trash. You use the complex and parsimonious solutions to prove the overall robustness of your findings. They help you pinpoint exactly which conditions are absolutely core to the outcome and which ones are just sort of peripheral contributors.
And just like that, what started as a chaotic sea of data is transformed into clear, logical, causal pathways. As Dr. Mira wraps up the session, she leaves the student with this ultimate takeaway. Truth tables organize your configurations, but it's Boolean minimization that actually reveals the simplest, sufficient recipes. The matrix has officially been unlocked. So now that you know how these engines work, and you know how to balance frequency, consistency, and theoretical logic, what hidden causal recipes are you going to uncover in your own data? Thanks so much for joining this explainer, and happy analyzing.